In this presentation, I am going to explain a rectifier control DC series motor and closed loop control of separately excited DC motor. Coming to the rectifier control of DC series motor, this is the circuit diagram. Input is a single phase supply. This is given to a half control single phase rectifier, and this is given to the DC series motor, and this is the equivalent circuit of the DC series motor. Ra is the armature resistance plus the resistance in series to the resistance of the winding, that resistance of the winding plus armature resistance, that is totally Ra. La is the armature inductance, and back EMF, small e is the back EMF, that is not a constant unlike separately excited DC motor. This is a variable one. It's called a function of the armature current Ia and omega M. Therefore, this is the equivalent circuit of a half control rectifier for series motor. Now the back EMF, the equation is, you know, that phi Zn divided by 60 into P by A, or phi into Z into omega M divided by 2 pi. Now the flux is not a constant. In a series motor, the flux is a function of the armature current. That is why flux is proportional to Ia, or the back EMF is equal to, it's a function of armature current into omega M. It is unlike a separately excited DC motor, that is a variable quantity. Even for a speed is constant, depending upon the armature current, the back EMF changes. Therefore, as armature current decreases, the flux reduces, and hence the back EMF reduces. And back EMF small e, that is E, is not constant and fluctuates with the armature current Ia, unlike separately excited DC motor. For a given speed, E is related to Ia through the magnetization curve of the motor, which is non-linear due to its saturation. Therefore, the motor magnetization BH curve, that will be that is based on that one, the value of this E will be changing, because E is a function of Ia, and the flux that is produced is basically depending upon the what is the armature current. Therefore, this is the voltage that is coming across the motor. This is the input voltage and is fired at a firing angle alpha, and that is until alpha to pi, the voltage across the motor is same as the input voltage. And at pi here, we are continuing a continuous conduction mode here. At pi here, the device, therefore during alpha to pi, the devices T1 and D1 are conducting. And at pi here, the voltage polarity reverses, input voltage polarity reverses, and the diode D2 is start to conduct. Since D2 starts to conduct, that will be applying a positive voltage here, or there's a reverse voltage across T1, and that gets turned off. And from pi to pi plus alpha, D1 and D2 are conducting. That is, the freewheeling diodes are conducting. Therefore, there will be a current flowing through the armature. There will be a current flowing through that one, but the voltage is equal to 0, because only the diode drop comes. So the voltage across the motor, that is VA, will be equal to 0 from pi to pi plus alpha. Again, pi plus alpha, T2 is fired. Then T2 is fired. Then what happens? D2 and T2 are conducting, and the voltage will become, it is equal to the minus of this input voltage, or that is the output voltage is, this is the voltage that is coming across the motor. Therefore, the devices that are conducting here, during this period, D1 and D2, during this period, T1 and D1, again D1 and D2, T2 and D2, like that one. These are the devices that are conducting for different duration. Continuing the rectifier control of DC series motor, this is the circuit diagram, and the corresponding, there are intervals are there. One we call it as duty interval, that is from alpha to pi. These T1 and D1 are conducting, and the voltage across the armature is same as the input voltage, that is from alpha to pi. That interval we call it as duty interval. And from pi to pi plus alpha, these devices D1 and D2 are conducting. That is the freewheeling period. During that period, the voltage will be zero and there will be a current through the armature. There will be current is there, and this is the current that is flowing through the armature, and the above one is showing the back EMF. This is the back EMF small e, and this is the current, and this is the output voltage, and these are the devices that are conducting for different duration. Now during the duty interval from alpha to pi here, the corresponding equation Vm sin omega t equal to RAIA plus LA DIA by dt plus, actually that is the back EMF. That back EMF is not a constant, it's a function of armature current IA into omega m. From pi to pi plus alpha, that is during the freewheeling period, the voltage is equal to 0. Therefore, that is 0 equal to RAIA plus LA DIA by dt plus function of armature current IA into omega m. That is the freewheeling period. Because of the presence of the term f function of IA into omega m, this is a nonlinear term. Equations are nonlinear and can be solved only by numerically. Because of this term, unlike separately excited DC motor, this function back EMF is a function of the armature current. Because of these terms, it can be solved only numerically. As a simplified method of analysis, what we are assuming that E is replaced by, we are assuming the average value of E, that is E is replaced by its average value, capital EA. We are taking the average value of this back EMF, and that we are assuming it is equal to EA, capital EA. And this EA is equal to then a constant Ka times omega m. Ka times omega m, where the constant Ka is a function of armature current. Ka equal to function of armature current. Actually, to get A, as you know that the BH curve, x-axis equal to H and y-axis equal to flux density. Or in terms of current, you can say that one x-axis, because H equal to Ni by L, therefore x-axis equal to current and y-axis equal to flux. Therefore, that curve, the BH curve, that is non-linear. Initially it is linear, but at once it is near to the saturation, it is equal to non-linear. Now, if you are calculating the slope of that one at any instant, that slope is the ratio of course, here flux divided by armature current. That constant, actually, that is a constant Ka. Ka equal to a function of Ia. And since the drop across the inductance, La, due to the DC component of the armature current is 0. Therefore, the average value of the voltage across the inductance is equal to 0. And then this equation can be written as the average value of the voltage that is coming across the armature, that is equal to VA, which is equal to the back EMF, average value of the back EMF EA plus IA into RA, where the average value of the voltage is given by Vm by pi into 1 plus cos alpha if it is a half control rectifier. If it is a fully controlled rectifier, it will be 2 Vm by pi cos alpha. Therefore, this is the equation relating the voltages, and the corresponding equation for omega m. Omega m is given by EA divided by Ka. Therefore, EA equal to VA minus IARA divided by Ka. And torque is given by Ka into Ia. Therefore, torque equation is equal to Ka into Ia. And these are the relation omega m and torque in the case of a series motor fed from a single phase, fully controlled or half controlled rectifier. Now let us see how can you determine the speed torque characteristics of a DC series motor for different firing angle alpha. Now this is plotted here, torque versus omega m for different firing angle. As firing angle increases, the curve is shifting towards left side, towards the center. Now let us see how can it be plotted. The first step is that calculate the speed torque characteristics. A value of Ia is chosen. We are first taking a certain value of the armature current Ia. Then corresponding to corresponding Ka is obtained corresponding to this armature current. The constant Ka is obtained from the magnetization characteristics, BH characteristics. That's what I told you. BH curve means y-axis equal to B and x-axis equal to H. This H is proportional to the current and B is proportional to flux. Therefore, BH curve is a curve representing the variation of the current versus flux. X-axis equal to armature current, y-axis equal to the flux. Now, the slope of that curve, that is representing as the constant. Therefore, from the BH curve, you can calculate what is the Ka. Once you calculate the Ka for a given this Ia, then you can calculate what is the torque. Torque equal to this, whatever this Ka into the armature current, what is chosen. And this is the Tk into Ia. For non-value of alpha, the average value of the Va can be obtained. As we have seen already, Va equal to Vm by pi into 1 plus cos alpha for a half control rectifier. It is equal to 2 Vm by pi cos alpha for a fully controlled rectifier. For a given alpha, you can calculate what is the voltage Va. Now, omega m can be calculated by this equation. Omega m equal to this Va minus Ia into Ra divided by K. Therefore, you can calculate omega m like this one and you can calculate torque like this one for different Ia, and that can be used to plot this curve torque versus omega m for different firing angle. Here I am going to explain closed loop control of separately excited DC motor or DC motor drive. Now, we have already seen that previous presentations. Below the base speed, we are using armature voltage control is used, and above the base speed, we are flux control. We are using field flux control is using. Therefore, below the base speed, right less than the rated voltage. I mean speed corresponding to rated voltage, but we call it as base speed. Below the base speed, armature voltage control is used, and above the base speed, field flux control is used. And this is the control block diagram in which this is the separately excited DC motor. Armature is fed from a control rectifier and field is fed from another control rectifier, and this can be either single phase or three phase based upon the rating of this motor. Now there are two loops here. One is called the inner loop, that is the current loop, and outer loop, that is the speed loop. Therefore, in this block diagram representation or control of this one, inner loop is the current loop and the outer loop is the speed loop. Now the drive will operate at constant field current and variable armature voltage below the base speed. That is, below the base speed control, we are using the armature voltage control, keeping the field current constant. And constant armature voltage and variable field current for the above the base speed. For the speed control of the motor above the base speed, we are using the field control in which the armature voltage is kept constant and we are controlling the field current. Therefore, both armature and fields are fed from a fully controlled rectifiers. There are fully controlled rectifiers are used. Continuing the closed loop control of separately excited DC motor, let us see the control below the base speed. Below the base speed, armature voltage control is used. Therefore, during this period, the field control loop back EMF is compared with a reference voltage E star. That is, this is compared with a reference voltage E star, which is chosen to be between 0.85 to 0.95 of the rated armature voltage. This is corresponding, this E star is taken corresponding to 0.85 to 0.95 to the rated armature voltage. And for speed below the base speed, field control saturates due to the large value of this error coming here, that field controller, that is a PI controller, that gets saturated, and the firing angle of the field rectifier, that is alpha B, is kept 0, applying the rated voltage to the field. Therefore, during the control less than the base speed, this is alpha F, that's the firing angle of this field rectifier, that means made 0, and we are applying the rated voltage to the field. For this ensures rated field current for the motor operation below the base speed. For below the base speed, you are applying the rated field current and we are controlling the armature voltage. When speed reference is increased, as an example here, the speed reference is omega m star, and here omega m is the actual speed. If omega m star is increased from omega omega m1 star to omega m2 star, if you are increasing the reference speed here, due to the large speed error, current limiter saturates. Because of the large error here, the large error coming here, the current limiter gets this error is coming. That is, a controller is the current controller is the, then there's a current limiter is there, that gets saturated, and sets the current to a maximum permissible value. This current is set to a maximum permissible value once it is getting saturated. Therefore, this is the reference current. This is set to a maximum value that is compared with the actual current, and this error is taken to given to a current controller. Again, it's a PI controller that is given to a firing circuit, and that is used to control the fully control rectifier. Continuing the closed loop control of separately excited DC motor, the drive accelerates at maximum available current and torque when the speed reaches to omega m2 star. That is, already we changed the omega m1 to omega m2 star. The current limiter desaturates and the drive settles to omega m2, and at this current, that gives the motor torque equal to the load torque. Like that, whatever the torque produced by the motor is equivalent to the torque demanded by the load. Now, this is the operation below the base speed. Therefore, by controlling this firing angle of this one, you are bringing the voltage to the required value and made to produce a required torque which is equal to the load torque demanded. Now, operation above the base speed, that is, we are using the field control, we are using field flux control. If the speed is set to above the base speed, the current reference is set to a maximum permissible value. Current reference is set to, that is, this current reference is set to a maximum permissible value, and firing angle of the armature rectifier, that is alpha, is reduced, and that increases VA initially, and motor gets accelerated, and E increases, that is back EMF increases, and the correspondingly, once the back EMF increases, the error also increases. That error increases, that is back EMF increases, means this error increases as the speed gets increased, speed above, this error is getting increased, and that is error is given to a field controller. Error increases and the field current continues to decrease until the motor speed becomes equal to the reference speed. That is, until the motor speed equal to the reference speed, the field current gets reduced and the speed is increasing. Therefore, speed becomes equal to the reference speed. Speed control above the base speed is obtained with the field flux control with armature voltage maintained at the rated value. You just understand that one at least. In order to run the motor above the base speed, we are controlling the field flux. Field flux is controlled, and during that period, you are applying the rated voltage to the armature. And in order to control the motor less than the base speed, we are applying the rated current through the field, and we are controlling the voltage across the armature. Therefore, this is the armature voltage control, and this is the field flux control.